Hey everyone, welcome back to the channel where we explore the latest in large language model implementations. Today, I'm thrilled to guide you through fine-tuning the cutting-edge Qwen3 model. This model offers impressive advancements in reasoning, instruction following agent capabilities, and even multilingual support. Best of all, fine-tuning is fully supported with Unsloth, a tool designed to make the process faster and more efficient, and resources from Unsloth show that all Qwen3 uploads leverage their innovative dynamic 2.0 methodology. This approach achieves top-tier performance on benchmarks like the 5-shot MMLU and KL Divergence tests, allowing you to fine-tune quantized Qwen3 models with minimal accuracy loss. Additionally, Qwen3 now supports a native context length of 128,000 tokens. The Qwen3 14B fine-tuning notebook is available via a Colab link, which you can find in the description. Unsloth enables the 8B version to train twice as fast, reduces VRAM usage by over 70%, and supports context lengths 8 times longer than other environments when paired with Flash Attention 2. Even the larger 30B A30B model fits comfortably on just 17.5 GB of VRAM with Unsloth. Next, let's see how the notebook shows the process of loading the model using Unsloth. It imports the fast language model from Unsloth and Torch for handling computations. The maximum sequence length is set to 2048 tokens. The data type is auto, detected by setting it to known, and 4-bit quantization is enabled to save memory. Unsloth provides several pre-quantized models for faster downloading and to avoid out-of-memory errors. For this tutorial, the focus is on the Qwen3 14B model with Unsloth's 4-bit quantization. The IMT notebook demonstrates loading the model and tokenizer using the fast language model's pre-trained loading function, passing in the model name, maximum sequence length, data type, and confirming 4-bit quantization. This prepares everything for the next steps. Now, the notebook illustrates how to add LoRA adapters to the model. This efficient technique fine-tunes only 1 to 10% of the total parameters, saving significant resources. Using a function from fast language model, the setup includes a rank of 16, targets specific model components like query, k value, and projection layers, sets an alpha value of 16, and disables dropout for optimal performance. Additional settings such as Unsloth's gradient checkpointing are used to reduce VRAM usage. The notebook uses the Alpaca dataset, specifically a cleaned version from Yama with 52,000 examples. This dataset follows a standard prompt format with an instruction, input for context, and a response. The end of sequence token is defined from the tokenizer to ensure the model knows when to stop generating text. A formatting function is created to structure dataset examples into the Alpaca prompt style, appending the end of sequence token. The cleaned Alpaca dataset is then loaded and formatted accordingly across all entries. Let's take a quick look at an example from the dataset as presented in the notebook. It includes fields for output, input, instruction, and the fully formatted text ready for training. Here's what the formatted text looks like for the first example in the notebook. The instruction is to give 3 tips for staying healthy, and the response offers practical advice. Alright, it's time to train the model. The notebook shows how to use a trainer called SFTTrainer from Hugging Face's TRL library. For demonstration purposes, training is limited to 60 steps to speed things up, but you can adjust it to a full epoch by setting num train epochs to 1. The necessary tools are imported, including training arguments from transformers and a helper from Unsloth to check for hardware support like Bafloat 16. The trainer is initialized with the model, tokenizer, and the prepared Alpaca dataset specifying the text field and maximum sequence length. Training settings include a batch size of 2 per device, gradient accumulation steps of 4, a small number of warm-up steps at 5, a learning rate of 24, and various optimization parameters for efficiency. The output directory is set to store results. The notebook displays current memory stats. It's running on a Tesla T4 GPU with a maximum memory of about 14.74 GB with around 11.9 GB currently reserved. The training process is then initiated with the trainer's train function. Unsloth makes this twice as fast for free fine-tuning with over 51 760 examples, a total batch size of 8 across the setup, and only about 64 million parameters being trained, less than 0.5% of the model's total. Let's let this run off until once completed, the notebook logs the training loss across the 60 steps, starting at 1.4606 and ending at 0.8782, showing a general downward trend as the model learns. Training is now complete. With training done, let's see how the notebook demonstrates running the model for predictions. You can customize the instruction and input, leaving the output blank for the model to generate a response. The same Alpaca prompt format is used for consistency. First, a feature in fast language model is enabled for twice as fast inference. For this example, the instruction is to continue the Fibonacci sequence starting from Qwen3 14B 8pi. The input is tokenized, prepared for the GPU, and the output is generated with a limit of 64 new tokens. Once decoded, you'll see the model successfully extends the sequence. The notebook also shows how to make the output appear token by token for a dynamic experience using text streamer from transformers. The Alpaca prompt is set up again. The model is prepared for fast inference, and the same Fibonacci sequence input is tokenized. The streamer is initialized, and the output is generated with a higher limit of 128 tokens, displaying each token as it's created. It's a neat way to watch the model generate responses in real time. Let's explore how the notebook handles saving and loading the fine-tuned model. To save just the LoRA adapters, the small changes made during training, you can either upload them online using Hugging Face's hub or save them locally. This doesn't save the entire model, only the adapters. The example saves both the model and tokenizer locally to a folder called LoRA model. You want to load these saved adapters for predictions later. The process is straightforward. The notebook demonstrates loading them back using the fast language model tool with the same settings for sequence length, data type, and 4-bit quantization. Once loaded, fast inference mode is enabled again. With the saved model loaded, the notebook tests it with a new instruction. What is a famous tall tower in Paris? This is formatted in the Alpaca prompt style, tokenized, and paired with text streamer to generate and display the response with a limit of 128 tokens. Initially, there's a value error due to some modules being dispatched to the CPU or disk because of limited GPU RAM. The suggestion is to ensure enough GPU memory or adjust settings to offload computations. Let's address this by restarting the session. Okay, I've restarted the session and rerun the necessary steps. Now, I'm loading them back and running the same question about the famous tall tower in Paris. The model loads successfully, and here's the response. One of the most famous tall towers in Paris is the Eiffel Tower. It is an iconic landmark of the city and one of the most recognizable structures in the world. The Eiffel Tower was built for the 1889 World's Fair and stands at 330 meters tall, making it the tallest structure in Paris. Perfect. And that's it. Thanks for watching, and I'll see you in the next video.